All right, good morning again. This should be the last set of lectures. I'm going to try and finish up the renal system or urinary system as best I can. I might have to do 2 videos because these things get too long. It's too hard to upload them. So I'm going to finish these today, which means, let's see, it's Wednesday. I won't be able to post them till Thursday. So there'll be last videos up Thursday. I'm going to give you one more short, I'm going to call it a quiz because it's not going to be big enough, probably 25 points. It'll be structure and function of the urinary or renal system. That's the last thing. So wrap up all those Learn Smarts, wrap up the last test. I think it's deadlines today anyway. And then you just have this one last test to do. I'll probably put it up Thursday or Friday. I'll have to leave it open through Monday, so you'll have a few days. But we got to do it quick because the semester's over. After Monday, the deadline, I'll go ahead and calculate your online portion of your grade. You already have the in-class portion of the grade posted. And then I'll just put down either your final percentage or the letter grade, depending on which Blackboard, whatever Blackboard will let me do. And then, of course, a day or so after that, I'll submit your grades. We're about done. Now, make sure you go ahead and do the Learn Smart on digestive. I'm not going to be able to get to digestive. It's not a very complicated system, but at least so you've hit the digestive system. That's what the Learn Smart's for, to make sure at least you've been exposed to it a bit. So let me finish up with the renal system as best I can. So we looked at kind of the gross anatomy of the kidney last time. We looked at plumbing, ureters, bladders, urethras. What we're going to do now is we're going to basically emphasize the nephron or the kidney tubule. I think I told you last time there's 10 million. There's about 1 million per kidney, 1.5 million. I think I had a 0 on the wrong spot in my notes. But so about 1 million nephrons per kidney. And again, the nephron is a functional unit of the kidney. All those functions we went over: red blood cell production, blood pressure control, pH, ion levels, eliminating waste. That's all the nephron. If you understand how the nephron works, just multiply it by 1 million, that's your kidney. So we sort of looked at a bit of the blood flow last time. I think I went through all the arteries, right? The renal artery, segmental, interlobar, arcuate, interlobular, or cortical radiate. And then the afferent and efferent arterioles that go into the capillary bed in the renal corpuscle, inside the Bowman's capsule. That's the glomerulus. That's where the filtration membrane is. So let me draw part of the nephron up here again. Let's see, I'm going to go like this. So I'll kind of scribble on the big screen here. And then I'll do a few things on the small screen with some better pictures. Let me put in the blood supply. So we had an afferent arteriole coming in. Let's go this direction, afferent. Then the glomerulus is inside here. And then the efferent is coming out. And what you've got is this efferent arteriole will split into another capillary bed that supplies the rest of the nephron. They're called peritubular capillaries. So this nephron will come out here and it'll move this way. And you'll get more capillaries. I'll go ahead and switch them to green. I already used blue. The efferent arteriole will split into peritubular capillaries, which are running next to the rest of the nephron. Peritubular. I'll get you a prettier picture on the small screen, but that's the basic idea. Now, the parts of the nephron. Let me go over them first and kind of show you their location. And then we'll go through the function. First of all, where these nephrons are located. Right about here. I'll put a little dotted black line here. This is kind of the junction between the cortex of the kidney. Remember, the cortex is that outer layer. And then the medulla, which is this big pyramid-shaped thing. So this represents kind of one renal pyramid here with the overlying cortex. The Bowman's capsule we looked at last time, that is always going to be up in the cortex. Now let me give you the names of the rest of the nephron, and then we'll go over the kind of different functional aspects of the parts of this nephron. We already did the Bowman's capsule, or the glomerular capsule. It's got a couple different names. It's not Bonans. I had it written wrong on the board. What's new? But that's the Bowman's capsule. I usually use Bowman capsule, not renal or glomerular capsule. I'm just used to Bowman's capsule, but either one will work. Remember, this is where filtration occurs. The high blood pressure in this glomerulus and the high permeability of the fenestrated glomerular capillaries and the podocyte cells making up the visceral layer of the Bowman's capsule have very high permeability. I mean, basically anything that's small enough will fit through. So everything will move out of the blood, except the cells, the larger proteins. Anything with a heavy negative charge doesn't get through as well either. So that's where filtration occurs. And again, we talked a little bit about controlling that blood pressure. The blood pressure in the glomerulus is very critical for maintaining glomerular filtration rate. And there are a couple of ways to control it. One was just that myogenic mechanism. If the blood pressure gets too high and you stretch out the afferent arteriole, the smooth muscle will reflexively constrict, increasing the resistance, dropping the flow. So that's one way. There's a second way, the tubular feedback mechanism. I'll get to that after I've gone through the parts, because that's going to require a few other interactions here. But it basically measures the filtration rate through the kidney and can monitor ion concentrations to increase or decrease filtration rate and blood pressure in here as necessary. So that's the Bowman's capsule. The next part, yeah, my diagram's kind of pathetic, but this part here, it's very close to the Bowman's capsule, so it's referred to as the proximal convoluted tubule. I'm going to abbreviate it to say room PCT. Proximal, because it's closest to the Bowman's capsule. Convoluted, because it's all twisted up, and it's a tubule. So the filtrate, as we'll see in a bit, is going to move from the Bowman's capsule. It'll move into the proximal convoluted tubule. Then there's a long, either loop of the nephron, I call it loop of Henle, just named after somebody. Either one will do. This loop of Henle dips way down into the medulla. You'll notice most of the nephron is up here in the cortex. Just that long loop of Henle dips way down into the medulla. Now, I will tell you, only about 20% of the nephrons have a really long loop of Henle dipping down towards the apex, the papillae of the renal pyramid. Many of the nephrons have much shorter loops of Henle. A few of them it's missing. So only about 20% of these nephrons have a long loop of Henle. They're called juxtamedullary nephrons. As we'll see, that loop of Henle is necessary to allow you to create a concentrated or hypertonic urine. All right, so you got the proximal convoluted tubule, loop of Henle. Then the loop of Henle has a descending and an ascending limb, they'll often call it, because fluid's going down here and up here, kind of intuitive. Then you get into the cortex, and there's another little twisted up section of nephron, and this one is called the, I'll abbreviate it, DCT is abbreviation for distal convoluted tubule. Distal just means it's furthest away from the Bowman's capsule, and it's also twisted up or convoluted, and it's a tubule. So the Bowman's capsule, proximal convoluted tubule, loop of Henle, distal convoluted tubule. And then this last bit, it's part of the renal tubule. Sometimes it's considered part of the nephron, sometimes not. This is called the collecting duct. The collecting ducts are fairly big, and there's actually not as many of them. You might have multiple nephrons all draining into one collecting duct. So there's actually going to be several nephrons that dump their contents into this collecting duct. Collecting duct is the only part of this tubule, this kidney tubule, that goes down through the medulla as well. So if you look in the medulla, all you're typically going to find is a loop of Henle and the collecting duct, which runs out towards the apex of the pyramid, the papillae, and then there's just an open duct there, and the fluid will just drain out of this right into the minor calyx. That's urine. That's going to go down the ureters, into the bladder, and you'll get rid of it. Now, as far as these parts of the nephron, just briefly, we've already seen what happens in the Bowman's capsule. This is pressure filtration. Basically, what happens in the kidney is almost everything in the blood is just removed, except for the formed elements, the large components. So blood cells shouldn't get into the Bowman's capsule. They shouldn't be part of the filtrate. None of the red blood cells, white blood cells, or platelets. And this filtration membrane also prevents most of the plasma proteins from moving across. So nothing big, nothing negatively charged. But everything else, the vast majority of stuff, all the water, all the ions, most of the nutrients, they can all freely move across this filtration membrane and end up in the Bowman's capsule. I think I told you last time it's like 180 liters a day you lose out of your blood into the lumen of the Bowman's capsule. Now, that filtrate has a composition that's about the same as blood minus the large plasma proteins in the cells. Otherwise, it's the same. You know, for example, if you had 0.1% glucose, I'll put a 0.1 and then do a little six-sided ring for glucose. 0.1% glucose in the blood, you're going to have 0.1% glucose in the filtrate as well. So it's basically very similar to blood plasma minus the proteins. That's really all it is. Now, the other problem you have here is the first step in urine formation is filtration. But as I mentioned last time, what does the kidney do? It basically takes everything out of the blood. The stuff you don't want, the stuff you want. You can't lose 180 liters of fluid a day for very long. You'd be dead. There'd be no blood volume. Blood pressure dropped to zero. So the first step in urine formation is this filtration, where you pretty much take almost everything out of the blood, put it in the lumen of the nephron. The next step, we're going to number them, step 2, is sometimes called tubular reabsorption or just reabsorption. And what this means, reabsorbs, you're going to take stuff that is in the nephron, and I'm going to put a blood vessel up here. Just going to cheat a little bit. This would be one of the peritubular capillaries, but this represents the blood. Reabsorption is taking material from the lumen of the nephron and moving it back into the blood. So you're reabsorbing it into the blood. Of course, the vast majority of what you filter out has to be removed back into the blood. If not, you'd perish. You'd lose much blood volume. So, for example, water. Your blood is mostly water. It's the biggest volume. Well, you can't lose that much water. So basically, all of that fluid that just went into the Bowman's capsule, almost all of it, 180 liters, you don't produce 180 liters of urine a day. God, you'd be dribbling all over the floor. Most of that stuff that's filtered out has to get reabsorbed. So, water. Most of the water you filtered out, you're going to reabsorb most of it. Nutrients. Do you want nutrients like glucose in your urine? No, you don't want to be inefficient with your nutrients. You might not find a dead antelope next week. So, you're going to reabsorb 100% of the nutrients. If you have 0.1% glucose in a Bowman's capsule, as you move through the rest of this nephron, by the time you get to the urine, there's no glucose in it. 100% of it has been reabsorbed. That goes for all the nutrients. Unless there's something wrong, you're going to reabsorb 100% of the nutrients that end up in the filtrate. You need them. Water, again, all of it, most of that. Now you have a little bit to play with. Some of the water, there's an obligate reabsorption of most of it. 90% of it. If you're overhydrated, that last 10% you can kind of play with. Some of it you can flush out. On the other hand, if you're a little dehydrated, you might want to reabsorb some more water. So you have kind of the final percentages you can sort of, in quotes, play with. That's what ADH is, we may look at later. If you're overhydrated, your urine will be fairly dilute. A lot of the water will still remain in the nephron. You'll flush it out with urine. On the other hand, if you're dehydrated, what ADH does, it basically causes the nephron to reabsorb additional water, move it from the urine back into the blood because you're dehydrated. Same with sodium. You have an obligate amount of reabsorption of a certain amount of sodium. The last bit, it depends. If you might reabsorb it if aldosterone is present, or you might let it stay in the filtrate and be secreted. So the last percentages you can sort of play with depending on the physiological state of your body. But most of what is filtered out, you have to reabsorb most of it. Again, things you don't reabsorb, you might leave like a lot of the urea in there and other substances that are nitrogen waste and so forth. That's going to stay in the filtrate. Whatever stays in the nephron and ends up in the collecting duct, that's going to be in the urine. But you reabsorb most of the other material. So reabsorption, moving material from the filtrate into the blood. You reabsorb most of the material, and reabsorption occurs in various places in the nephron. You get some reabsorption here in the proximal convoluted tubule, luminal penduli, distal convoluted tubule. There can be reabsorption anywhere, but the bulk of it, I think like 65% or so, the majority of reabsorption occurs immediately after the Bowman's capsule. Most of the reabsorption occurs right off the bat in the proximal convoluted tubule. Then you get some other additional absorption in other areas of the nephron. And reabsorption has several components. You can see it described as an active and passive reabsorption. Certain substances, for example, sodium, they're active transport pumps in the cells of the proximal convoluted tubule. They have a lot of surface area, a lot of microvilli. They're metabolically very active because they got a lot of active transport pumps, need a lot of ATP, have a lot of mitochondria. Things like sodium, they're active transport pumps, constantly moving sodium from the filtrate back into the blood. Then there's passive components of reabsorption, like water. Initially, water is isosmotic in the filtrate in the blood. They're about the same osmotic strength. So how are you going to move water? It's not easily actively pumped, can't use facilitated diffusion. How are you going to move it if it's already isotonic? Well, when you actively transport the sodium across, think about it, as you're moving sodium out of that nephron, what's left is a lot of water. So it'd be like having a little container of salt water. If you could move out just the sodium ions, what's left in the cup is going to be more and more water. Basically, that's why they say when you actively transport sodium, water will typically follow, not always, but mostly. That's because as you reabsorb the sodium, you're making this fluid more dilute or hypotonic, and then it will follow by osmosis. So you actively pump the sodium. That's the most actively moved substance here. When you actively transport sodium, water is going to follow passively, just by osmosis. And a few other things will happen. As the water keeps leaving by osmosis, all the other solutes start to get concentrated, and then they'll start just moving by diffusion. That's sometimes referred to as solvent drag. So you got active and passive components of reabsorption. Now I'm going to skip the loop of Henle this time. I'll probably pick it up on the last video. So loop of Henle, as I've already mentioned, that's used to allow you to concentrate urine. Humans can make urine that's from 50 milliosmoles to about 1,200 milliosmoles. Again, a milliosmol it's a number of dissolved particles per liter, thousandth of an osmol. Blood is about 300 milliosmoles, to give you an idea. Distilled water is about 40 milliosmoles. Salt water is about 14 milliosmoles. So your urine can be as dilute, almost as fresh water. 50 milliosmoles, that's just water, almost. You know that when you're overhydrated, you urinate a lot. What's it look like? Looks like water. It's mostly water. So you can have very dilute urine. On the other hand, if you're dehydrated, how much urine do you produce? Not a lot. And what's it look like? It's really dark colored. That's because your kidneys have the ability to reabsorb much of the water. And if you're a bit dehydrated, the urine you produce starts to get almost as concentrated as seawater. Not quite, but it's pretty concentrated. 1,200 milliosmoles is what? 4 times more concentrated than your blood. You need the loop of Henle to produce that concentrated urine. And let me get back to that so I don't make the video too long. Yesterday's took 6 hours to upload, so I'll skip the loop of Henle. Let me just briefly talk about the distal convoluted tubule. All right, the distal convoluted tubule. Again, there's some reabsorption occurs there. It's mixed kind of everywhere. But one of the things I'll use the distal convoluted tubule to describe is tubular secretion. Tubular secretion, you can think of it as the reverse of, or the opposite of reabsorption. In tubular secretion, material is going to be moved from the blood up here in the peritubular capillary. It's going to be transported into the lumen of the distal convoluted tubule, the nephron, which is going to allow it to be secreted. Why do you do this? Because sometimes, you filter out material, much of it gets reabsorbed, you may need to secrete additional amounts, and it can depend, like potassium. We talked about potassium with the endocrine system earlier. Potassium levels get just a little bit too high, your heart stops, your nervous system stops, tends to be kind of detrimental. So you normally filter out potassium, much of the potassium gets reabsorbed, but what if potassium levels are a little bit too high? Again, we talked about aldosterone earlier in the semester. This is where aldosterone, or something like aldosterone, can have an effect. If your blood potassium gets a little high and aldosterone is released from the adrenal cortex, the aldosterone is what will cause excess potassium to be moved from your blood into your nephrons so you can flush it out with urine so it doesn't interfere with your excitable membranes. Other things that are secreted, many drugs, chemicals, I think opioids, aspirin, penicillin, those are automatically secreted by the kidney. Again, that's why on many of those medications you have to take repeated dosages because the kidney keeps pulling them out of the blood and dumping them in your urine so they don't persist very long. Hydrogen bicarbonate ions. This is a way you can control the pH of your blood. You can selectively secrete, sort of different ratios of hydrogen ions versus bicarbonate ions to help regulate pH of the blood. If it's too acidic, start secreting excess hydrogen ions. It's too basic, don't secrete the hydrogen ions, secrete some bicarbonate ions. So tubular secretion is moving material from the filtrate or from the blood back into the filtrate. And then once it's dumped into the filtrate, it will leave out the collecting duct. Once it's out of the collecting duct, it's just urine. Now let me hit a couple things on the small screen. I'll be back. Alrighty.
This is a diagram, kind of like I got on board, just prettier. And they're showing you a couple of nephrons here. This is the arcuate artery and vein. This area is the cortex. Below it here, this is a medulla. In this yellow structure, this is showing you a nephron. There's a Bowman's capsule. Proximal convoluted tubule is here. Here's your loop of Henle. This one has a fairly short loop of Henle. This example has a very long loop of Henle dipping way down in the medulla. Then you have the distal convoluted tubule draining into the collecting duct, which is going to go down and eventually exit out the renal papillae, out some ducts. So those are the different components. Let me run back a bit. Here's an enlargement. This is one of our models, but this is showing you the glomerulus, and this is part of the Bowman's capsule here. That's proximal convoluted tubule. What they're showing you here, this is the visceral layer of the Bowman's capsule. These are those podocyte cells with the little slit openings right there between those little podocytes. This is a visceral layer of the Bowman's capsule. They've stripped it away over here so you can just see the glomerular capillaries, which are also fenestrated, have lots of holes in them. So this lumen of the Bowman's capsule here, this is where the filtrate would collect at 180 liters. Here's your afferent arteriole. Blood goes through at high pressure through the glomerulus, and fluid leaks out, ends up in here. Again, everything but the blood cells and the plasma. What's left goes out the efferent arteriole. And let me look at the peritubular capillary. So here's an afferent arteriole, goes into the glomerulus. Here's the efferent. Then what I couldn't show well on my diagram, all these other capillaries, these are the peritubular capillaries right here. They supply, everything but the Bowman's capsule and glomerulus. These capillaries are surrounding the proximal and distal convoluted tubule. That's where secretion and reabsorption can occur. All right, we'll take a little bit break here. Alrighty, this is a diagram. These are on the PowerPoint. They're already posted. But this is real simplified, showing you the nephron. Here's all the tubes straightened out. There's the Bowman's capsule. There's the glomerulus, efferent arteriole, peritubular capillaries. And it's just giving you a quick rundown, which is kind of all we've done. Not a lot of detail. But glomerular filtration creates, the filtrate, which is a lot like plasma minus the formed elements and proteins. Tubular reabsorption, it removes, all the useful stuff you need to keep. All of your nutrients, 100% reabsorbed, most of the water, ions you need to retain, that sort of thing, moves them back into the blood. Secretion is taking additional material from the blood, like potassium, penicillin, other waste, and it secretes them into the nephron for release. And then the water conservation we haven't gotten to yet. But I think I'm going to stop at that point. The last thing we'll do, we have to go over producing concentrated urine, and I'll go over the tubular feedback mechanism for controlling glomerular filtration rate and look at the juxtaglomerular apparatus, and we'll probably call it quits there. I'll go post this. Take care.